Hello, class. This is Mr. Hart, and in this podcast, we want to start the Simple Machines chapter of our textbook. And before we can really understand what simple machines are and what they do, we need to understand a term called work. Okay, so what is work? You've probably said to yourself before, "I need to work on something, or I need to get some work done, or I need to get to work." Okay, but what does that really mean? Okay, when we say work, well, it may have a different definition when we're just talking among friends and among people, right? But in physics, it's a very specific definition of work. Okay, so the amount of work we do on an object, okay, is defined by the following equation. Okay, the amount of work that is done is equal to the force that is put on the object times the distance that the object travels. Okay, so for example, going back to this guy pushing the car, the amount of work that he does on the car is based on how much force he's putting on the car and how far the car travels. Okay, so you just take the force he put on the car, take the distance that the car moved, that would be the work. Okay, so a question to think about is if your car is stuck in the snow and you're pushing and pushing on it, are you doing any work? Well, the answer would be no, according to physics, because you're not moving any distance, right? So no work is being any done. It doesn't matter how much force you're putting on the car or the object or whatever it is, no work is done because there's no distance that is traveled. Okay, so keep that in mind. This is going to be very important when we talked about simple machines. Okay, work equals force times distance. Okay, so let's look at the 6 simple machines that you should know. You may have learned these in elementary school, but let's just go back through them just in case. So there's 6 simple machines. There's a lever, there's a pulley, there's a wheel and axle, there's an inclined plane, there's a wedge, and there's a screw. Okay, so all 6 of these simple machines help us with work. Okay, and how they help us is they don't change the work that we have to do. We still will do the same amount of work, but they make it easier for us to do it. Okay, so there's a couple of things a simple machine can do. First of all, they can change the size of the force when we do work. Okay, so let's say we're doing a certain amount of work. Okay, so we may need to change the amount of force we want to put on an object. Okay, either we want to make the amount of force very small or very large. Let's say we want to make the force very small because we're not very strong, for example. But what it's going to do is instead of having a large force, we're going to have a very large distance. Okay, so the same work is going to be done on an object. Let's just think of like a crowbar or a lever of some kind, right? You may need to move some tile out from the floor, or pry open a piece of wood, or pry open the floor where the wood is and something like that. Pry some nails up. Okay, you need to do some work, but you don't want to do as much force, right? Because it's harder to put a lot of force. So we want to change the distance. So you think about the crowbar, for example. Here's maybe the wood you're trying to pry up from the floor down here. Here's the crowbar. You're going to have to move that crowbar a very large distance, right? You're going to have to swing it around in order to pry that up, but you're going to get a lot more or a lot less force that you have to do, right? You just have to move the crowbar instead of pry up the floor. Okay, so the same amount of work is going to be done, but to you, you have to put less force and you have to do more distance, but you much rather do the more distance than do a lot more force. Okay, another thing you can do is it might change the distance that the force is applied for. Okay, so think of like a broom, for example. In that case, you want the broom to move back and forth. Okay, here's the broom. Okay, you want that to move back and forth a large distance, right? But you don't want to move that much. You want just to move a little bit of distance up here, right? And so you are going to apply a larger force, okay, a much larger force on the handle, but only for a very small distance, okay? And so now you only have to do a small distance, okay, or only have to move a small distance, but you have to apply a larger force, but then you get the same amount of work done, okay? So we kind of have this balance of how much force are we putting on, how much distance are we moving, okay? But we still use the same amount of work or do the same amount of work, okay? So simple machines don't change the amount of work we have to do. They just change how we use the force and how much distance we move it, okay? And then the last thing they can do is they can change the direction of the force. Think of like a pulley, for example. Instead of having to pull up on the rope, you are pulling down to move something upwards. Okay, so it changes the direction you have to move the object. Okay, so it can do one of those 3 things. So let's start with what we were just talking about. Okay, and that's a lever. Okay, so there's lots of applications of levers. We talked about a broom, for example, is a lever. You may have seen a catapult, that's a lever, okay? Hammers, things like that, they're all levers. And so what the lever does is it's a machine that can change the direction and the force, or the direction of the force and the size of the force, okay? So think about this hammer. It's a lever, okay, because here's the balance point of the lever. You would be pushing in this direction, right, or pulling in this direction on the hammer, and it's going to push up on the nail like this, okay? So it changed the direction of the force, right? You are pulling this way, but the force went upwards. Can also change the size of the force. So you have to move the hammer a large distance, right? But you don't have to put nearly as much force on the hammer to get this nail up, okay? And then every lever has two parts. It has a bar, okay? And it has a fulcrum, okay? A point at which it balances on, okay, or pivots around. In this case, the fulcrum would be actually the hammer head right here, okay? That's the point which it pivots about. And so any type of lever is going to have those two things, okay? But again, it's just for changing the direction and changing the size of the force, okay? In class, we looked at a simulation that kind of shows this property with a teeter-totter, right? If you balance people out on the teeter-totter, you have to use more distance the lighter the object is, okay? But it's easier to balance. So this kid is 4 times as far away as this guy right here, but that's because he's a fourth of the weight. And so the farther out you go, the less weight you need or the less force you need, okay? Let's look at a couple of examples of the different types of levers that you'll see. The first type of lever is what we call a first class lever, and that's where the fulcrum is in the center. This is probably what you think of when you think of a lever, okay? Like a teeter-totter or something like that, okay? You have force on one side, load on the other side, okay? The force is pushing down, which actually moves this upwards, and that pivot point is in the center, okay? So things like a teeter-totter, for example, are an example of a first-class lever, okay? A second-class lever, you have the load in the center. So you'll have the force on one side, you'll have the fulcrum on the other side, and the load is in the middle, okay? Think of like a wheelbarrow, for example, okay? That's an example of a second-class lever. You have the all the material, if you're, carrying sand or gravel or cement or whatever it is in the wheelbarrow, it's in the center, right? You're holding onto the handles on the edge, and the wheel is on the other side, okay? And the last example, which you probably already guessed, the third class lever is when the force is in the middle of the lever, okay? The load is on one side and the fulcrum's on the other, okay? And so in all these examples, it's based on what's in the center of the lever. Is it the fulcrum, is it the load, or is it the force? Okay, so let's look at a couple of examples and see if we can determine what type of class lever these are. Excuse me. So take a minute, pause the video if you want, and see if you can figure these out for yourself before we go through them. Okay. But if we look at this, let's start with the broom. Okay. In this example, let's think about what's in the center. We have the load down here. Okay. We have the force right here, and we have the fulcrum at this point on his hand. Okay, so in this case, the force is in the middle. That means it's a third class lever. Okay, the wheelbarrow, like we talked about, is a second class lever, right? You got the load in the center, force on one side, the fulcrum on the other. Okay, a catapult would be an example of a third class lever, again, because you got the force from the elastic right here, you got the load on the edge, and then you got the fulcrum down in the base. Okay. A hammer, in this use of the hammer, would be a first class lever because we got the force up here on the handle, we got the pivot down here, and then we got the load, which is the nail. So this is a first class lever. Okay. Nail clippers are going to be a third class lever again. You got the fulcrum down here. You got the, these aren't nail clippers. These are tweezers. You got the fulcrum right here, you got the force right here, and you got the load up here. So again, the force is in the middle. So this is a third class lever. Okay, and then last of all, a pair of scissors. This is actually 2 first-class levers put together, okay, because you got the fulcrum in the center, you got the force on the outside, and you got the load on the other side. Okay, so this is a first-class lever. Okay, so hopefully that makes sense. If you need more practice, you can find other examples of levers and see if you can determine what type of class they are. Okay, let's move on to pulleys. So you're probably already familiar with what a pulley is. It's just where you have a wheel of some type and rope basically going around it. They use this wheel and rope generally just to change the direction of the force. Instead of having to pull something straight up, you are pulling down. Okay. If multiple pulleys are used, the size of the force can be changed as well. We're going to look at that in a second. And then some pulleys are movable along the rope. Okay, think of like a zip line, for example. The zip line actually moves along the rope instead of the rope moving along the wheel. Okay, so there's a couple of different types of pulleys, just like there was different types of levers. There's what we call a fixed pulley, which is where it's generally what you think of, where you have the pulley staying where it's at, the load's on one side, and the force is pulling down on the other. Okay, you can also have a movable pulley, like a zip line, where the load is on the pulley itself, and then it moves along the rope. Okay, and then you can have like a block and tackle pulley, or just what I would call a complex pulley, basically, which is just where you have many pulleys put together. Okay, these block and tackle pulleys can actually lift very large loads because not only do they change the direction, but the many pulleys themselves can help support some of that weight. Okay, so again, you have to pull the rope a farther distance, but you have to use less force. Okay, so again, this is an example where it helps with that changing the size of the force. Okay, another interesting thing to think about is in this example, the fixed pulley. There's no difference in the work that's done. It's just changing the direction, right? You're using the same amount of force. You're pulling the same distance. It's just changing that direction of the force. In this case, with the movable pulley, it actually does change this amount of force, okay? Because you will only need to use half the amount of force to pull this up. The reason why is that half the rope over here is supporting the weight, and your half of the rope is supporting the weight, okay? And so the amount of force you'll need to use is half as much, because this side will help you lift this movable pulley. But then again, what's the trade-off? You have to pull this rope twice as far to move this up, okay? And so again, still the same amount of work, but you have to use less force, but more distance. Okay? All right, then we got wheels and axles. Okay, you probably are familiar with this one as well, but there's many examples. A Ferris wheel, just tires on a wagon. You may not think about it, but a doorknob is a wheel and axle. Okay, gears count as wheel and axles. Okay, so if we look at the definition, it's just two cylinders that share the same center. Okay, and both cylinders rotate about the same point and in the same direction. And the inner cylinder is the axle and the outer cylinder is the wheel. Okay, so if you just look at this wheel, right, this is the wheel on the outside. This part right here on the inside is the axle. Okay, and so this can become, or this helps with work because not only does it change the direction and keep it moving when you are rotating something, right, but the larger the wheel you have, the easier it is to push. Okay, but then again, the larger wheel you have, the more distance that it's going to have to travel or going to have to move. Okay, so it always goes back to that work equals force times distance. Okay, so a wheel and axle, what it does is you can use less force to rotate the wheel, but then again, you'll have to use more distance. Okay, and that's usually a trade-off that you want. Okay. Other examples of simple machines, the inclined plane. Okay, is just basically any ramp. It's a sloping surface connecting a lower elevation to a higher elevation, okay, from the ground to the moving truck, for example. And the shallower the slope, the more efficient the inclined plane. And that makes sense, right? You'd much rather travel along this plane than a plane that's shaped like this, okay? You'd much rather go to something that's nice and shallow and smooth, right? You wouldn't want to travel up something that's steep. And so the shallower it is, the more efficient or easier it is to travel along that inclined plane. Okay. And again, just any type of ramp. Stairs, I wouldn't count stairs as an inclined plane. They're kind of a variation of an inclined plane, but just any flat ramp I would usually consider an inclined plane. Okay. And then we have wedges. Okay, and their efficiency comes from helping you again change the direction of the force. They're usually made for separating things like knives or hatchets. Okay, a chisel, for example. And so if you think about a wedge, it's really just two inclined planes that are stuck together side by side. And again, its main purpose is just to change the direction of the force. You put the force downward with the hammer or the mallet, whatever it is, and then that force is put outwards from the wedge. Okay, so it changes the direction of the force that you were putting in. So it's very useful for splitting things apart. Okay, and so you put force in one direction, outputs in another. Okay, and then the last one is a screw. Okay, and a screw is usually made just for holding things in place, but there are other applications. And if you think about it, it's just an inclined plane wrapped around a cylinder. Okay, you can imagine this, inclined plane just twirling around the screw. Okay, and its job is to change a rotational force into a directional force. So you rotate the top of the screw, for example, but the screw will actually go downward into the wood, right? So it changes that rotational force into a directional force. Okay, and again, it's usually made to hold objects together. So things like bottle caps, screws, all those are made so that the object stays in place. Okay. All right. So the last thing I want you to do is to pause this video for a second and see if you can identify what these simple machines are in these pictures. Okay. After you've had a chance to look through that, let's go through them. Okay, so this, for example, would be a wedge, right? Because they're chiseling away. They are separating the tile from the floor. Okay, that's a chisel. He puts force in direction, or he puts the force in one direction, and it outputs in another. Okay, so that's a wedge. That counts as a wedge. Okay, a bottle cap. Okay, that would be a screw, right? Because it screws onto the cap to hold it in place, so nothing comes out. A pry bar or a crowbar, that can be considered a wedge or a lever. I would consider it more of a lever. You may wedge it in initially, but then you will pull down on the bar as a lever. Okay, a hatchet would be a wedge, again, because it's made to split the wood. This would be an inclined plane, rolling the barrel up. You might even consider the barrel a wheel and axle. This would be a pulley, right? The pulley that puts the flag up onto the flagpole. And then this roll of toilet paper would also be a wheel and axle because it has an axle in the center and then the wheel on the outside. Okay? All right, and then in class we did the Simple Machines home lab, or I assigned that to you as homework. But that's it for this podcast. Hopefully that all made sense, and let me know if you have any questions.